Hey everybody, we're going to go through Polygons 5 here. There are 6 lessons in the Polygons chapter. We are getting really close to the end of the chapter, so let's just power through it. We are going to break away from parallelograms for a second. We have taken several lessons and we have talked about parallelograms and then specific types of them, like a rhombus, like a square, or like a rectangle. So today we're going to go over things that are none of the above. So now we're going to talk about a trapezoid, which you could probably have guessed because that was the first set of pictures. And then we'll get to the other part here in a second. So anyway, we should probably start with what a trapezoid is. A trapezoid is a quadrilateral with, and the key here is the word exactly, one pair of parallel sides. It has to be exactly one pair of parallel sides. So basically, if it was 2 pairs of parallel sides, it would be a parallelogram. And if it had no parallel sides, then we would just have to call it a quadrilateral. We wouldn't really have a lot of good options there. Okay. I suppose we could also get to what we're talking about here a little bit later, but I'll just save that. All right, so I want to give you 2 examples of what a trapezoid would look like, and the first example is not as common as the second. People don't necessarily look at this and think to themselves that this is a trapezoid, but it is. It has a pair of parallel sides right here and right here. And then what we have going on, that right there is going to be a leg, just like this will over on this side. And then I don't know if you remember this from back in your formula days where you were trying to do area of certain figures back in algebra class. But a trapezoid actually has 2 bases. Both of these red arrows point to a base. The reason I bring up the area formula is the area formula for a trapezoid uses base 1 and base 2 because it just depends on your perspective. If you were to take that figure and you were to flip it over, then suddenly now the bottom is different. So we can't really just say, oh, that's a base because it's on the bottom. You have to think about it either way. All right, now, we also should get into the more traditional, I guess you would say, picture of what a trapezoid would look like, which would be something like this. This is the one that most kids identify with a lot quicker. We still have the parallel bases right there. But this time, it looks a little bit more traditional because now you've got this side and this side right here and right here. If you ever end up with a figure that has one pair of parallel sides and then the other pair is congruent and it's not a parallelogram, then you would get something that looks like this. And I'm just going to name it for you real quick. This is called an isosceles trapezoid. And I think one of the ways that you can sort of visualize best why we call it an isosceles trapezoid is because if you were to take this and then go beep, 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 there you go, you would have an isosceles triangle. So basically, if you can visualize an isosceles triangle, then you can also visualize an isosceles trapezoid. All right. Now, real quick, I want to go over some of the math that is involved here. Example 1, we need to solve for x. If we have an isosceles trapezoid, I want you to think about the angles. Whenever you're talking about an isosceles triangle, you're talking about 2 congruent angles because there are 2 congruent sides. That same concept is going to apply here. So we have a 47 and a 47, and we're actually also going to use that concept up here where we're going to have an x and an x. So if we wanted to set up an equation for this really quick, you could say 94 so 47 plus 47, plus 2x equals 360. Every single quadrilateral in the universe has interior angles that add up to 360. All right, so if we take away 94 from both sides, you're going to get 2x equals 266, which means x would be 133. Now, there are theorems that help us remember this, but when we get to example 2 here, what I want to see is if anyone can get it right without the theorem. So if you have a guess, just pause the video. If you don't have a guess, that's okay too. But I want to see if you could just use common sense to get this right really quick. All right, so if you didn't pause the video, or if you paused it and now you're playing again, let me show you what's going on. This right here, this segment right here is splitting the trapezoid right down the middle. It is basically breaking up the trapezoid into two smaller trapezoids. And since it is right down the middle, that means it is the average of the two lengths that we have. Like we have a 20, we have a 5. This segment that I am pointing to is the average of the distances here. It's halfway in between the 5 and the 20, so it makes sense that the distance would be halfway in between 5 and 20. Now, when you do an average, all you have to do is add and divide by 2. 5 plus 20 is 25, and half of 25 is 12.5. So the length of that segment is 12.5. All right, so let's get to the actual theorems involved here. Jot them down. They're not going to be too ridiculous. The second one is longer than the first, so you may have to write small at a certain point here. The first theorem, that's going to explain example 1. If a quadrilateral is an isosceles trapezoid, then each pair of base angles is congruent. That's why we had 47 and 47, and that's why we had x and x. It kind of goes back to that idea of how isosceles triangles work. Okay? All right, now the second theorem. This one's going to be a little bit longer. I may have to shrink down my font. You may have to write a little bit smaller. If a quadrilateral is a trapezoid, the midsegment is parallel to the bases, and its length is half the sum of the lengths of the bases. So what actually happened here is, it is a trapezoid, so we have parallel sides here and here. It turns out that midsegment was also parallel. So it actually reminds me quite a bit of how we dealt with midsegments of triangles in the previous chapter. It will be parallel and half the length. That's how it worked with triangles. With trapezoids, it is parallel and half the sum. So when you take the two parallel sides that go with it, you add them and divide by 2. Remember, dividing by 2 is the same as taking half. You get what you're looking for. To me, it almost reminds me of common sense here, just in the regard that you've been averaging things for a very long time. If somebody asks you to average two numbers, you almost always get it right. So it makes sense that you would get it right here as well. All right, let's jump into the last figure we're going to deal with here. We're going to talk about a kite. A kite is a quadrilateral with two pairs of consecutive. Now, this is where it gets different. instead of the opposite sides being congruent, the consecutive sides are congruent. In fact, you're not allowed to have the opposite sides be congruent at all. All right, so let me show you what this would look like. Basically, what we're getting here is a figure that looks kind of like this. We're going to have, I mean, most people pretty much know what to expect out of this because they've seen a kite before. You grew up, you had a kite, or something like that. All right, so essentially what's going on here is these two are congruent, these two are congruent, but the opposite sides are not, as in these two are not, and these two are not. Okay. Now there is a theorem that goes along with this, and you could actually combine it with what you already know to make a little more sense of the deal. And the theorem is actually going to be similar to what we did with a rhombus. If a quadrilateral is a kite, then its diagonals are perpendicular. Now my sketch was a little bit off, so if this picture ends up being a little bit less than perfect, that's okay. There you go. Boom. All right. In a kite, the diagonals are perpendicular. So I guess that brings up the point, well, how are we going to know whether it's a kite or a rhombus? You have to make sure that the sides are different lengths. Because again, in a rhombus, all four sides are going to be congruent. In a kite, that is not allowed. All right, so we'll do two examples and then wrap up. Example 1, solve for x. Now, the reason I bring up the idea of the diagonals being perpendicular is because it sort of helps us get a visual for just what's going on here. You don't have to draw this on this particular problem, but I think it's kind of nice. You can actually see the relationships. So if you're looking and you're kind of wondering, well, why is it that he's doing what he's doing on this problem? I just want to illustrate it for you in terms of the diagonals being perpendicular. What we've created here is the HL theorem, which is why I can show you these angle relationships. All right, so I'm going to clear this out because I need more room. That doesn't mean you have to erase it. I just want to show it to you. If you look, because we know the angles are the same here and here due to the HL theorem, I could actually sneak in a 124 right here. And then I could just say that 124 plus 32 plus x, and I know that's a lot of writing, you might not be writing all of that yourself, equals 360. Combine those numbers, you get 248 plus 32 would be 280 degrees. And then we just subtract and we find out that x equals 80. So it turns out x equaled 80 degrees in this picture. So again, knowing that that was 124 is the key to getting this problem right. And the only reason I knew it was because we have congruent angles, which I could ultimately prove from back in the day using the whole HL idea. All right, let's try that one more time here. We have 87, we have 144. And if you're wondering what other angle needs repeated, I can just say, well, these diagonals are perpendicular, which means I have the HL theorem going on. And if you can't guess it or if you can't see it, I'll just give it away right here. We need to put an 87 right in that spot. Okay, once again, you can kind of tell we have two markings and one marking and an 87 in the middle. So we're going to have two markings and one marking and an 87 in the middle. All right, so if you add up all four and put it equal to 360, I'll kind of jump right to it here. We have 87 plus 87 is 174 plus 144 is 318. and that means x equals 42. That does make sense. That looks like a smaller angle right here, so it shouldn't surprise me too much that we have a 42 right there in that spot. All right, so now that we've made it through trapezoids and kites, we're almost done with this chapter. Appreciate you listening, and I'll see you next time.